All right, we're ready to move on to our next section of Chapter 8, which is actually going to be the next two sections of Chapter 8. We're going to kind of put it all together because it all has kind of the same type of information that we want to kind of talk about. And so in the last section, we talked about similar polygons. We talked about how to show whether they're similar or not by showing every single side's proportional and every single angle is congruent. So all the corresponding parts had to match up accordingly. We talked about scale factor, we talked about ratio perimeters, ratio of areas. Now in this particular section, or these two sections here, we're going to focus primarily on triangles. So if I'm given two triangles, how can I show that they're similar to one another without having to go through all of the different pieces? So we're going to talk about the shortcuts, kind of like we did with congruent triangles in the past. So in this case, we're just going to start in with the different theorems. And so we talk about angle-angle similarity. If I have two triangles, I can show that they're similar if I know two of the angles are congruent. So that's what this whole statement here says. If two angles of one triangle are congruent to the corresponding angles of another triangle, then the triangles are similar. So if I can show that two angles of one triangle are the same as two angles in another triangle, we're good to go as far as whether they're similar or not. We don't care about the side lengths in this particular instance. So this is one of the shortcuts we can use. I don't have to show all the sides are proportional and all of the angles are equal. Two angles is enough. So if we look at a picture like we see down here, one thing that should stand out right away is vertical angles. Just like what we did with congruent triangles at the end of last semester, we're going to kind of do the same thing with these in that we need to be able to show that different pieces match up or correspond. And so we're going to look for things like vertical angles and shared sides, or vocabulary terms like midpoint or bisect. And so those are things that are going to come into play again, but now we're talking in terms of similarity as opposed to congruence. So right there's one set of angles. Now the next thing you should be keying in on is the fact that there's these little triangles on the outside here. Anytime they put triangles on lines, that tells us that those two lines are parallel to each other. So they're telling us that line AB is parallel to line CD. Anytime we look at parallel lines, we should automatically be looking for alternate interior angles. This is another thing we really tried to harp on you guys at the end of last semester that you're looking for with parallel lines. We're looking for alternate interior angles. And so if we look here, we can match those up. We have angle B right here. Now alternate interior means we come across the transversal, so from one parallel line to the next. And if I look for alternate interior, that means I need to go opposite side of the transversal inside the two lines. So angle B and angle C are going to pair up. So we got angle AEB congruent to angle CED through vertical angles. And then we got angle B congruent to angle C by alternate interior angles. Now at that point, I have two sets of angles, one set here, the other set here. That's enough to say that the two triangles at this point are similar. So now I just got to be really careful with how I name them. So triangle AEB will be similar to triangle. So here I got to be careful. A is the only unmarked angle, so it matches up with D. E matches up with E, and then B matches up with C as we have it marked. So making sure you write the correct statement is going to be important. So making sure the order lines up. And then once we know the triangles are similar, we need to say how. And so they're similar by angle-angle similarity. And so this is what your answers on these types of questions should look like. What are the two triangles that are similar if they ask for the statement? And how did you know? What shortcut was available for that particular problem? So in this case, two angles gives us angle-angle. The next theorem is called SAS. Now this is going to be very similar to what we saw with SAS in the last semester when we talked about these types of problems. And so SAS is two sides, but this time the sides must be proportional. That's a really key thing here. It's not that the sides are congruent because we know that one triangle is bigger than the other, but the sides are proportional. And then the included angles must be congruent. And so included, remember, is that word for in between. So we want the angle that touches both sides given or is in between the two sides given. And so if we look at the two triangles down below here, what we notice is we have this angle marked congruent to this angle. Now, as I'm looking at that then, those two angles are in the appropriate spot for SAS. If I look here, I've got side, angle, side. Their angle's in the middle between the two sides. Same thing over here. We have side, angle, side. We're in between. Now what we have to check though is even though their angles are marked congruent, we need to make sure the sides are proportional. We need to make sure that they divide out to be the same number. And so when we do this, we got to be really careful here that we match up the appropriate sides. So whether it's a reflection or rotation or whatever it might be, we have to make sure that the sides match up appropriately. So on this one, it's a matter of just matching up small with small, big with big. So my smallest side over here is 12. I'm going to match it with the smallest side from the other triangle, 3. And so if I take 12 divided by 3, I get 4. Then I check the other two sides. 16 is my larger side here, match it up with the 4 here, so 16 divided by 4, I get 4. If I divide and get the same number all the way through, then that tells me the sides are proportional, and now these two triangles are similar by SAS. So two sides proportional that come out to be the same ratio, and the angle must be in the correct location in between the two sides. Our third theorem, or shortcut, is side, 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 and this is pretty straightforward. Just like before, where all three sides had to be congruent, now we're talking similar figures. One shape's bigger than the other. All three sides have to be proportional, so it's kind of like what we did on the last slide, but with all three sides. We're going to take each side that corresponds, divide them out, make sure they all come out to be exactly the same number. And so if we look at these pictures below, we, again, go with the same thing where we try to match things up. Smallest side from one matches with smallest side from the other. So 3.2 and 9.6 go together. Now, if I do this, it doesn't matter what order I go in. So if we want to stick with big over small like we've been doing, I take 9.6 divided by 3.2, and that's going to come out to be 3. And so then I look at my next two sides, and so I can pick any two sides from here. So the biggest side in the next triangle is 18, match it with the biggest side in the other triangle, 6, and I just divide them out. 18 divided by 6 is 3. And then my last two sides go together, the middle ones, and I have 14.25 divided by 4.75, and if I divide those out, I end up with 3 again. So I notice all three divide out to be exactly the same thing, so these two triangles are similar by side, side, side similarity. So it's a matter of matching up the correct sides, so making sure small with small, big with big, and then medium with medium, and then just making sure they all divide out evenly. Okay, so if we use this, it should be, given a particular situation or given a particular picture, should be pretty obvious which of the theorems you should be going for. So which shortcut should we be going for based on the information in the picture? So for instance, on this one, we know that all three sides are given, so we should be looking at side, side, side similarity. So all we have to do is match up corresponding parts appropriately. So the smallest side up here is 7, goes with the smallest side down here, 21. So if I divide those out, 7 divided by 21, I can go to decimal or reduce it down as a fraction. So 7 over 21 goes to 1/3. And then I can go around this, do the same thing with all the pictures. So the next biggest side is 10, matching with the next biggest side, 30. So 10 divided by 30 is 1/3. And then I match up the last sides, 15 with 45. And 15 over 45 goes to 1/3. And so I notice all three ratios are exactly the same. So my two triangles are similar. So now when I name them, triangle QPR, for instance, is similar, use the correct symbol here, is similar to triangle. Now I've got to be careful. So QPR, Q ran through the square, and then P to R ran through the triangle. So I want to go from N through the square and then through the triangle, so NMO. And again, we'll check to make sure that the order matches up. So QPR is similar to NMO by, in this case, side, side, side similarity. So that's what we're looking for there. So I want to see this right here, that you checked all the ratios. I want to see this right here where you have the statement, and then I want to see this, which tells me exactly how they're similar to one another. So 3 big things that you need to make sure you show in these types of problems. If we look at another example here, based on the information given, we have two sides along with one angle in the picture. So chances are we're looking for SAS. Now, as I look at the sides, smallest side 10 matches up with smallest side 8. If I divide those out, 10 divided by 8, and again, we can do fraction form or we can do decimal form. So 10 divided by 8 is 1.25. And then I match up the other side, 15 with 12, big with big, so 15 divided by 12. If I divide those out, I get 1.25. Now the sides are good to go then. Both came out to be exactly the same ratio. The angles are congruent to each other. But the thing I've got to be really careful with here is if I want SAS, the angle has to be in between the two sides. And if I look here, this angle J is not in between. I would need angle I for that. And the same thing over here, 75 to here is not in between the two sides, which would be angle E. So in this case, we go back to our not enough information abbreviation. So they might be similar to each other, but we can't tell based on what they give us. We don't have SAS because the angle's not in the right spot. So we got to be really careful with that and make sure we don't get fooled. Just because it's two angles on one side doesn't make it SAS. Now this next one is a little bit trickier problem sometimes in that two of the triangles that we're looking at are overlapping with one another. And so what I have to realize here is what I'm really looking at is I have this little triangle KLP. I'm just going to draw another little triangle off to the side here. So triangle KLP here, which had a side length of 8 and 12. And then a larger triangle, KMN, that had a side length of 10 and 15. So that's what the numbers they gave us here, 8 and 12 for the little triangle, and then 10 and 15 for the big. Now what I'm looking at here is if I want these two triangles to be similar, I notice that they gave me two sets of sides. And then I also need to make sure that I am aware that since these are overlapping, this is kind of a new freebie that we get with this type of question. I notice that angle K is the same angle in both triangles. It's a shared angle, kind of like we had shared sides last semester with our congruent triangle. So we're saying this angle K here and this angle K here are exactly the same angle because in the original picture, they were the same corner. So what I have here is the setup for SAS as long as my sides are proportional. So I've got 8 matching up with 10. So if I take 8 divided by 10, I can reduce it or plug it in my calculator, and we get 4/5. I have 12 matching up with 15. And so if I take 12 over 15, I get 4/5. And so I've got the same ratio for both sets of sides, which means triangle KLP is similar to triangle KMN by SAS similarity. So when you're looking at these types of problems, especially with these overlapping triangles, it sometimes helps to draw the two triangles separately so you can list out all the different side lengths and things like that. And then just be aware that if they ever overlapped at a corner, those shared angles are now something we want to be on the lookout for with these types of questions. Okay. Last thing here is just kind of a review of what we talked about in the first section. So once we know triangles are similar, what are things we can do with them? And so one of the things we can do is solve for missing pieces. So it says a flagpole casts a shadow that's 600 inches long. So I've got this flagpole in the picture, and it casts this shadow, which they say is 600 inches long. At the same time, a woman standing nearby who is 64 inches tall. So this woman standing right here is 64 inches tall. She casts a shadow that's 40 inches. What we want to know is how tall is the flagpole. So how tall is that flagpole to the nearest foot? In this case, we're going to go actually in inches. This hasn't been changed yet. So if I notice here, basically what's happening is I've got these two triangles. So when I kind of highlight the different pieces here, I got these two triangles that are going to be similar to each other. And so I can match up corresponding parts. I can match up the height of the flagpole with the height of the woman, x over 64. And then I can match up the shadow lengths, 640. And so if I go in the same direction with the flagpole shadow versus the lady shadow, I set up my proportion. This is exactly what we did in that last section of setting up similar figures, getting the proportion set up, and then cross-multiplying and solving. So if I cross-multiply here, I get 40x is equal to, if I take 600 times 64, I get 38,400. And so then if I divide both sides by 40, I end up with a value of 960 inches. So the flagpole would be 960 inches tall. So with these similar figures, once we know that they are similar, using angle, or side, and stuff like that, we can still use the processes from our first section and actually solve for missing parts, whether that's missing angles or whether it's setting up proportions and solving for missing sides like we did here. So with that, you should be able to work on today's assignment, which is going to be a worksheet. Just like with any other worksheet, you need to make sure that if you are in class, you'll get a copy of it. If you're not, go to Google Classroom and get a copy of it. And then make sure you ask questions. Ask in class, email, check the answer key once it's available, make sure everything looks good, and try to get that done and ready to turn in when we ask for it in class.